This project explores real-time path planning using trajectory libraries. Path planning is a core problem in robotics, and a great example is RoboCup, an autonomous soccer competition. Speed is crucial in this game, and taking inefficient paths, or sitting and thinking for more than a split second, will get your team left in the dust. Interestingly, these robots are limited more by their acceleration than their top speed, which means that the fastest path is not necessarily the shortest path. There are two main approaches to this problem right now: rapidly exploring random trees, RRT, or trajectory optimization. RRT is great at finding the shortest path, but it's difficult to express the physics of the system, such as maximum acceleration, so many of its paths can actually be slow or impossible for robots like ours. Trajectory optimization can easily express the physics of the system by adding them as constraints to an optimization problem, but it can take a very long time to run. Our solution is to use trajectory libraries. The first step is to discretize all possible initial conditions. The second step is for each initial condition, we build a library of possible paths to take. Then lastly, at runtime, we select the fastest path for our goal that doesn't hit any obstacles. This approach gains the efficiency and accuracy of trajectory optimization, but can be run hundreds of times faster. Every possible goal having its own library sounds like a huge amount of work, but we can use symmetry, spatial invariance, and bounds on our conditions to map down to just a few dimensions, and then discretize it into a few samples. For our case, we can cover the entire space with only 35 libraries. To build these libraries, we do trajectory optimization around a set of canonical obstacles to push the path in many different directions. The more diverse our paths are, the more likely one of them will be able to get around the obstacles. Here are a few examples of our libraries from different conditions. In order to quickly select a path from our library at runtime, we keep each library sorted from fastest to slowest. First, we pick the library that's most similar to our actual goal, and then check the paths one at a time for collisions with the obstacles. As soon as we find a path that works, we can stop searching because we know it's the fastest. This is extremely fast, and it takes an average of 1.8 milliseconds to run. However, our paths are slightly less efficient than optimal, and occasionally all of our paths will be blocked by obstacles. When tested over 1,000 runs, our algorithm found a solution 98% of the time, and on average was only 4% slower than pure trajectory optimization. As you can see in the histogram, there are some rare cases where a solution is 20 or 30% slower, but for the most part it performs very well. Overall, our algorithm runs hundreds of times faster than trajectory optimization, allowing it to be run in real time, while only sacrificing 4% of optimality and 2% of feasibility.